Hello math learners, topic 15, second order linear inhomogeneous ODEs with constant coefficients. So in this section we'll discuss solving second order linear inhomogeneous, so no longer homogeneous. You can also say just non-homogeneous. ODEs with constant coefficients as given below. So here's our second order linear differential equation with constant coefficients, and what makes this inhomogeneous is that this will be equal to some non-zero expression on the other side, some function of t, potentially a constant. Now let the function g of t that's over here is called the forcing function for reasons which are discussed later in this unit. Let y sub g of t represent any particular solution to this inhomogeneous ODE with forcing function g of t. The word particular solution, we've used general versus particular. A general solution has constants in it that are unresolved, that they have constants that no matter what the value of the constant is, you're looking at a solution. A particular solution is a specific solution that meets certain conditions. So we're using the word particular here in that sense. So let y sub g be any particular solution to the inhomogeneous ODE with forcing function g of t. Now we're going to use a method called the method of undetermined coefficients. So I'll explain a little bit more what that is exactly. I'll demonstrate it here, but then we'll talk more in detail about it. To find a particular solution to the linear inhomogeneous ODE below. So here's our linear second order differential equation with constant coefficients. And the fact that we have a non-zero function on this side makes it inhomogeneous or non-homogeneous. Okay, what we're going to do is we're going to assume, well, first of all, let's refer to this function over here as our, you can call it whatever letter you want, we'll call it g of t over here. So we're trying to find y sub g of t. We want to find any solution to this differential equation that has this particular forcing function. And we'll use y sub g to refer to it. And we're going to assume that y sub g of t has this general form, but with an unknown or undetermined coefficient, hence the name of this method. So we're going to assume that y sub g is going to be some unknown coefficient. We can put capital A, or I'm going to use lowercase letters, an unknown coefficient times this g of t function structure, so e to the negative 3t. With this assumption, we're simply going to plug this into this differential equation and then see if we can determine what a has to be so that the equation is satisfied. So we need to get a couple derivatives. Let's do y sub g prime. The first derivative will be negative 3a e to the negative 3t. And the second derivative will be 9a e to the negative 3t. So there are our first two derivatives. Now we're going to plug it into the differential equation and see what happens. So we'll start by rewriting y double prime, which is 9a e to the negative 3t, plus 3 times y prime. Y prime is negative 3a e to the negative 3t, plus 2y, and the y prime, y term is just a e to the negative 3t, so we're going to double that, plus 2 times a e to the negative 3t. And all of this should be equal to, in the end, 4 e to the negative 3t. Now, because the derivatives all involved e to the negative 3t, it's possible that this side will collapse and just become this side. We just have to figure out what a has to be to make that happen. And looking at, let's see, so we're going to simplify this expression next. So we have, I'm also going to factor out the e to the 3t. So I'm going to do a couple things at once. So we just have 9a to start, minus 9a, and then plus 2a. And all of this was multiplied by e to the negative 3t. And that we want to be equal to the other side of this, equal to the forcing term. The e to the negative 3t's can be divided out. We effectively, and 9a minus 9a cancel, so we really just have 2a must be equal to 4, which tells us that a must be 2. So we found that if y sub g as a function of t is equal to 2e to the negative 3t, that this is a particular solution to the ODE. Now this ODE, we do not have any initial conditions specified. And I know that we've been reserving the term particular solution for when we go from a general solution to a specific solution that satisfies the given conditions. That's when we said particular. But the word particular solution really just means non-general. And this is a non-general solution to this ODE. Now, we don't know whether it's going to satisfy any sort of initial conditions yet, but we certainly know that it satisfies the differential equation. I leave it you to verify that when you plug this in and do all the derivatives that the ODE is satisfied. Okay, now we focus on creating a general solution to a linear inhomogeneous ODE with constant coefficients so that if we do have initial conditions, we can determine the constants that will satisfy them. So suppose that y sub g is a particular solution to the ODE without initial data, and y sub 1 and y sub 2 are the solutions to the corresponding homogeneous ODE. So we'll go back to the homogeneous ODE, which has y1 and y2 as independent solutions. I should have mentioned here that these are the independent solutions. Then the general solution of the ODE is given below. So we take the particular solution to the inhomogeneous solution plus a constant times y1 plus a constant times y2, where y1 and y2 are the linearly independent solutions to the homogeneous version of the ODE. Okay, so let's do this one here. We've already shown that y sub g for this function is 2e to the negative 3t. Here we did that in the last slide. Now let's go back to the homogeneous version of this. So rewrite the differential equation, but switch the other side to 0 again, and find out what the solutions to the homogeneous version are. Well, the characteristic polynomial will be lambda squared plus 3 lambda plus 2 is equal to 0, which factors lambda plus 2 and lambda plus 1, which gives us two roots, negative 2 and negative 1. So that means our y1, our first solution, is e to the negative 2t, and our second linearly independent solution is y2, which is e to the negative t. Right? So do your e to the lambda t and your e to the lambda t for your two different lambdas. So now if I take all three of these, I can construct the general solution. Let's write it right here. The general solution is the particular solution plus some constant times y1 plus some constant times y2. Now what would happen if I plugged this function into this differential equation? Well, these parts will zero out. If you take only this and plug it into this differential equation, you'll get a 0 as a result, because e to the negative 2t was a solution to the homogeneous version. If you take this term and plug it into the differential equation, you're going to get 0 back, because e to the negative t was also a solution to the homogeneous version of this differential equation. When you plug this part in, this particular term, notice there's no constant in front of it, take that and plug it in, you're going to get 4e to the negative 3t. So this is the part here that guarantees that the 4e to the negative 3t will come out correctly, and these parts will zero out when you plug them in. But what they do is they give us the generality that we need so that we can satisfy any initial conditions that might be presented to us, which is what we want to do next. So let's do a derivative. We need to get a derivative here so that I can do my y prime information. So the derivative of our general solution is negative 6e to the negative 3t, minus 2c1 e to the negative 2t, minus c2 e to the negative t. And now we're going to plug in 0 for y at this, 5 for y. Right? 5 is y when t is 0. So 5 for y. Let's make a system out of this. 5 goes in for y, at the same time 0 goes in for t. So giving me 2 plus c1 plus c2. And now we're going to plug in into the derivative 0 for y prime, at the same time t is 0. So that's going to give us negative 6 minus 2c1 minus c2. And let me give myself a little bit more room here. Move this over, shrink that down slightly. Okay, just give myself a little more space. Let me just go ahead and hide that. Make sure we have plenty of space here. Okay. Now we want to solve this system here for C1 and C2. Notice that if you add the two equations together right now, the C2s will cancel. So that's effectively what I'm going to do. Add the two equations together, and we get 5 equals -4 minus C1, and the C2s cancel. Now solve for C1, and we're going to get C1 equals -9. All right, now we're going to find C2. If C1 is equal to -9, you can plug it in right here. And we have 2 minus 9 is -7. Add that -7 to this side, we get C2 is 12. So we can now write our particular solution 2e to the -3t plus C1 is -9, so it's going to be minus 9e to the -2t. And then C2 is 12, so plus 12e to the -t. All right, now, so we're using the word particular in two cases. This was a particular solution to the ODE, but ignoring the initial conditions. All right, so we're calling this part here a particular solution. When you plug it in, you satisfy this differential equation, and it was particular in the sense that there were no constants here. I should be looking right here. There are no arbitrary constants attached to it. It had to be that specific function that satisfies this ODE. But this function alone would not have satisfied these initial conditions. Right? Look at that function only and plug in 0. Right away we get a contradiction that y of 0 has to be 5. So the particular solution to the inhomogeneous differential equation is not general enough to satisfy any initial conditions. That's why we got to add these two terms here at the end and then find out what C1 and C2 are to create a new particular solution. Now, the one I'm currently highlighting, which is the answer we just found, is a solution to this differential equation as well as it satisfies these initial conditions. So this is the one that we wanted ultimately to find. Okay, now the next slide is a table that's going to help us know how to make an initial guess for a trial solution for determining the y sub g, the particular solution to the inhomogeneous ODE with forcing function g. And here, our initial guess was just some multiple of the function that we have here, 4e to the -3t. Okay, so if your forcing function is a polynomial, we'll use p of t to stand for a polynomial, then the trial solution you should do is a general polynomial of equal degree. And I'm going to use q to stand for that. So if your forcing function was 6t plus 5, then you would want a general which is a first degree, then you would want your q of t to be at plus b. And then figure out what a and b have to be. Okay, if your forcing function is a polynomial times e to the rt, remember this polynomial could just be a constant. It could be a 0-degree polynomial. So this covers this case right here. This is a polynomial times e to the some number times t. It's a 0-degree polynomial, 4, times e to the -3t. So we have this case here for constants or polynomials involving powers of t times e to the rt. Now, if r is not equal to either of the roots of the characteristic polynomial, then your general form is going to be a polynomial of the same degree, general polynomial of the same degree, times e to the rt. This is the strategy we used in the last example. Let's examine what I mean by that. So our forcing function was a 0-degree polynomial, 4, times e to the -3t. So my guess was a arbitrary 0-degree polynomial, a, times the same exponential. So all I did is I made that polynomial become arbitrary but same degree. So the 4 became an a. If the r, that's the coefficient of t in your forcing function, happens to be one but not both of your roots of the polynomial, the roots of the characteristic polynomial, not this polynomial, not the p's and q's, but the characteristic polynomial. That's what these lambdas are, by the way. Maybe should have made that more clear in this slide, but the lambdas are the roots of the characteristic polynomial. And since we're working with second degree, you're going to have either two real roots that are different, two real roots that are the same, or two complex roots that are complex conjugate pairs of each other. Those are the only possibilities when you're working with the second degree. So if this r in your forcing function matches one of the two one of the two roots of the characteristic polynomial, but not the other, then you're going to have to do an arbitrary polynomial of equal degree as the p of t, so q of t again, times e to the rt, and then times an extra t. Now if the r that's in your forcing function exponential here equals both of the roots of the characteristic quadratic polynomial, so in other words, if they have the same real root that's repeated, and that's the same as the r, then what you need to do is multiply t squared with an arbitrary polynomial of equal degree as p times e to the rt. And you're going to get your undetermined coefficients will be in these polynomials right here. Like if this polynomial is first degree, then this q will be at plus b. It'll be an arbitrary first degree. If this polynomial is second degree, then your qt's will be at squared plus bt plus c. All three qt's will be that. And you have to figure out what those coefficients are. Next case, what if your forcing function is the general form of a polynomial times an exponential times a sine or cosine of bt? And we're going to assume that b is non-zero here. Because if b was 0, then our roots would be real, not imaginary. But so we're assuming that b is non-zero, so we do have imaginary roots to our characteristic polynomial. And if the a and b in your forcing function match the a and the b, or say don't match the a and the b entirely, so this a has to be that a and this b has to be that b. If your expression here does not perfectly match this, then we create a, we're calling this a trial solution by doing the following. You're going to do an arbitrary polynomial of equal degree as the p of t polynomial here, so I'm doing q of t, times e to the at times cosine of bt, plus another polynomial, so I say q1 and q2, another polynomial is arbitrary of equal degree, times e to the at times sine bt. So we start to get much more complicated in setting up our trial solution. Now, if the a and the b in your forcing function match the a and the b from your complex conjugate roots of the characteristic polynomial, if they match perfectly, then you're going to have to take the previous trial solution and multiply everything by a t. So you're going to have an extra t in front of here and in front of here. Okay, we're going to see some examples of all this here in a moment. This flow chart can feel kind of confusing when you first are exposed to it. And then the other one is if your forcing function is a combination of other functions, so some alpha times f plus some beta times h, and you happen to already know what your particular solution would be for just f or for just h, so y sub f and y sub h, then you can reconstruct you can get your new particular solution by doing alpha times y sub f plus beta times y sub h. This is called the superposition principle, and we're going to show you how that works in our very last slide. Okay, so there's a lot of material here on this slide. We're going to come back to it a few times as we move forward. Now for some examples. Construct a trial solution for each linear inhomogeneous ODE below. Okay, in order to determine whether or not we have to first determine what all of our lambdas are so that we know effectively which portion of this table to look at. So we're going to have to find the characteristic polynomial and find your two lambdas, your two roots of it. So before you even look at this side, first thing I want to do is say, okay, this is a lambda squared minus a 4, and this has two roots. Lambda is equal to 2 and negative 2. Now the other side is a polynomial. It's a 0-degree polynomial. So actually I didn't even have to find the lambdas, because for polynomials we just do the same. We just do this top row. So if you have a polynomial forcing function, then you want your trial solution to be an arbitrary polynomial of equal degree. So this is a 0-degree forcing function. So we want our, and let's assume that over here is, all of these functions over here are the g of t's. So I'm going to use g as my subscript. So our y sub g of t will just be an arbitrary constant. That's it. Here's another example where we have a polynomial. It's a higher degree this time. It's a 2nd degree. I'm not going to bother finding the lambdas here, because when we have a polynomial on this side, we just create a particular solution with undetermined coefficients by doing a polynomial of equal degree as our forcing function polynomial. So we're going to do a 2nd degree with arbitrary or undetermined coefficients. So I would use this as my guess for a solution. And then we would do it like we did before. I'd take this, I'd plug it into this differential equation and try to figure out what a, b, and c are, so that we wind up getting this expression as a result. Next case. Okay, so now we're starting a venture where we have polynomials times exponentials, and a polynomial times exponential. So all of these are the polynomial times exponential. We have 1st-degree polynomials, and then we have a 0-degree polynomial. And so looking at our table here, we're now in this part of the table. So in order to know which of these 3 rows I should look at, I definitely need to find, all your lambdas. So we're going to want to, let me go ahead and just get rid of that. We never had to do it for that one. The characteristic polynomial here is lambda squared plus lambda minus 6, which factors to lambda plus 3 times lambda minus 2. So we get 2 different lambdas, 2 and negative 3. They're both real and they're not repeated. Now we look at the r, that's in the exponent of our forcing function. It's a 4. 4 is not either one of these. Right, so if we look back at our table, we're in this category, because the 4, which is our r, was not equal to either of our one of our roots of the characteristic polynomial, which means we're going to follow this format for doing a trial solution, where the q is the same degree as whatever polynomial is in front of our e to the rt. Okay, so looking at this, we have a 1st degree in front of here. Is it okay if I'm just going to stop writing y sub g? We don't need to write any of that stuff for this, because it's technically included in our header anyway. So we have a characteristic, or we have a 1st degree coefficient of this e to the 4t, so I'm going to have to do a 1st degree general, so at plus b, that's my q of t, times the e to the 4t. And I don't need to put any t's in front, because the 4 there, the 4 that's in that exponent right there, the 4, does not match either one of our roots of the characteristic polynomial. Okay, this next one is going to be different. Right, this is the exact same left side of the differential equation, so we get the same 2 lambdas, 2 and negative 3. And negative 3 does match one of them, but not both. Right, so the r matches one of my lambdas. So that puts us in this category, where the r is one of the lambdas, but not the other. So we have to do the same thing we did before, but we need an extra t in front. So I'm just going to copy this one here. Of course, the 4 is going to be a negative 3 as well. That's not a 4 any longer. Right? This 4 here matches that 4. It's the r. So this has to match the r, which is that negative 3. But we do need an extra t in front, because negative 3r matched one of, but not both of, my lambdas. All right, this next one's a different differential equation entirely. So we have a lambda squared plus 6 lambda plus 9. That factors to lambda plus 3 times itself. So we have our lambdas are negative 3 and negative 3. And this time, our r matches both of them. Now, if this had been a 4 and not a negative 3, then it would have been this same answer. This would have been right here as well, if that were 4, because it would not have matched either of the lambdas. So you could go straight to this. But because this r matches both of them, that puts us into this category right here, where the r is equal to both. So we just need to put an extra t squared in front. So we're going to have effectively this, but we need this front to be t squared. All right, let's do this some more. Now I have sines and cosines involved. All of these have sines and cosines, which put us into this part, potentially, of our table. Now, if there's no exponential involved, it just means a is 0. It means that there would be, these parts here would also be gone. So we just have to match our forcing function. Our forcing function is 6 sine 3t. That matches this one right here, where the 6 is the 0-degree polynomial in front. The a is 0, so that's just not visible. And then we have the sine of 3t. Okay, now let's get the lambdas for this. This is going to be lambda squared plus 4, which when you solve it, you get 2 different lambdas. You get lambda is equal to plus or minus 2i. So I'm going to emphasize the 0 there. So our lambdas have the form 0 plus or minus 2i. The a is 0 and the b is 2. Well, look at our forcing function. Our forcing function, you could write it as 6e to the 0t times sine 3t. And the 0 matches the 0. So that part matches, but the 3 and the 2 don't match. So we don't have perfect matching of our a and b in our forcing function with the a and b of our roots of the characteristic polynomial. Part of it matches, the zeros match, but not the 2 and 3. So according to our table, our lambdas are not equal to a plus or minus bi, where the a and b are these letters here. I should really say this one here, because we had a was 0 and b was 2. Sorry, I take that back. B was 3 in our forcing function, but in our lambda it was 2. So our lambdas do not match these a plus or minus bi. So we are going to use this row with the a's are 0, so these e to the at's will not be there, but the b's will be 3's. It'll match the 3 that was here in front of our sign. And then we got to look at our polynomial in front. The polynomial is a 0 degree, so I got to make sure I put arbitrary 0-degree polynomials in front of each of these. Okay, so what is that going to look like? An arbitrary 0-degree polynomial is just a times e to the 0t times cosine of 3t. And then plus an arbitrary polynomial of degree 0, so that's the b, times e to the 0t times sine 3t. And this becomes our trial solution for finding a particular solution to the inhomogeneous differential equation. So you would take this, you would find 2 derivatives, plug that in for y double prime, add 4y to it, and then see if you can determine what a and b are, so that you wind up getting just a plain old 6 sine 3t. Okay, the next one, y double prime plus 4y, so the same 2 roots of the characteristic polynomial, 0 plus or minus 2i. And this time we are going to get perfect matching, because you could rewrite, let me move this over, you could rewrite our forcing function as negative t, so there's a polynomial, times e to the 0t times a cosine of 2t. Right, so our forcing function falls into this class right here. So now we just have to compare the a and b that we're seeing in the forcing function to the a and b of our lambdas. And we get perfect match this time. Right? The a's are the 0s, they match, and the b's are 2s, they match. So because we get a perfect match, we have to use this bottom one, which is going to be the same basic structure, but with extra t's in front. So we're going to have to put, let's look back here at our example. We have a first-degree polynomial in front. So we're going to have to let our q's be first-degree arbitrary polynomials. Then we're going to have to do an e to the 0t, which will be 1, and a cosine of bt. which will be cosine of 2t. And then e to the 0t, which will be 1, times the sine of bt, which is our sine of 2t. And then we'll put the t's in front. All right, so here's what this looks like. Arbitrary polynomial of degree 1, at plus b, times e to the 0t times cosine 2t, plus an arbitrary polynomial, so ct plus d. Notice I'm not saying a and b twice, because they don't have to all be the same, times sine 2t. And because we had perfect matching of the a and b from our forcing function and our characteristic, the roots of our characteristic polynomial, we must also put an extra t in front of each of these. So this becomes your trial solution. And this gets much more and more complicated, because to differentiate this, you're going to have to do several product rules. And then differentiate again, several product rules. So you get quite a complicated expression over here, and then you have to figure out a, b, c, and d are all of them, so that this winds up being the result. We're going to do some examples of finding the constants. Okay, the next one. Here now we have an exponential and a trig present, and we have first degree polynomials in front. Let's see what our solutions to the characteristic equation would be. We have lambda squared minus 2 lambda plus 5. You're going to have to do the quadratic formula on this. Okay, let's maybe do that work. I'm going to just do that work, and then I'm going to erase it. So we have negative b, 2 plus or minus square root of b squared, which is 4, minus 4ac, so that's minus 20 all over 2a. That's going to be 2 plus or minus square root of 16, that's a 4i, all over 2. So 1 plus or minus 2i are our roots. 1 plus or minus 2i. Let me get rid of that now. Okay, so looking at this, do we have, you can ignore the polynomial in front for the time being, but compare the e to the e to the negative t and the sine 2t. So the a here is a negative 1. It's the coefficient of that t, but that's not the same as this one. But the b's is 2, and the b is also 2. So we get, again, a partial match. The 2's match, but the a and the negative 1 don't match. So that puts us, as far as our table is concerned, into this category. The a and the b from our from our forcing function do not match the a and the b exactly for our roots of the characteristic polynomial. So we're in this realm here. So we're going to have this construction. Okay. So let's begin with we have a first degree polynomial here in front. So I'm going to begin with an arbitrary first degree polynomial, at plus b, times e to the at, where a is what's in front of, it's matching this expression here, so negative t. Be careful that the a you're using here is the a from the forcing function, not what you would call the a from the root of the polynomial, characteristic polynomial. So make sure your a's and b's are coming from the forcing function, not from your roots. And then times a cosine of 2t, and then plus, let's move this over, another arbitrary first degree polynomial, ct plus d, times e to the at times sine 2t. And this is our trial function. You'd have to do several derivatives. It gets more and more complicated, a bunch of two derivatives here, plug it into this differential equation. I don't know why I was circling up here. Plug it into this differential equation and see if you can figure out what a, b, c, and d are, so that we wind up with the forcing function in the end. Okay, one more. This time we have a slight variation of the differential equation on the left. We are going to get lambdas are going to be negative 1 plus or minus 2i this time. So our forcing function is part polynomial, first degree polynomial, part exponential, where a is negative 1, which matches this a, and then part trig, sine or cosine, with a b, 2, that matches this b, 2. So here we do have the bottom case again. The a and b from our forcing function match the a and the b from our complex roots of the characteristic polynomial. So we're going to have to add the extra t's in front. Other than that, it's going to look a lot like we just did up here. But you're going to need an extra t in front and an extra t in front. Okay, that's how you make use of this table to come up with a trial solution for determining what your particular solution to the inhomogeneous ODE is going to be. And then once you do that, you can then determine what those coefficients are that are required. Okay, so now let's go ahead and let's let the rubber hit the road now. We're going to finish out some problems, or at least find general solutions to some problems here. We'll begin by finding the particular solution. Notice we just have a polynomial on this side, so I don't need to worry about finding the roots of the characteristic polynomial at first. But I'm going to have to find them eventually anyway, because they're used to help create the general solution. So let's go ahead and let's just do that now. Yes. Lambda squared plus 9 is equal to 0 is our characteristic polynomial, and we get lambda is equal to plus or minus 3i. Okay, now let's go to our, so this tells me that the y1 will be cosine 3t and y2 will be sine 3t. Right? These are your linearly independent solutions to the homogeneous version of this ordinary differential equation. But now we want to figure out what our particular solution is to this inhomogeneous version. Just debating my space here. Okay, I'm going to do that right here. So let's assume that we can refer to this as g, if you will, or you can use a different letter, f. But our y sub g will be equal to, this is just a second degree, so we want a general second degree polynomial. So at squared plus bt plus c. It's good to put a little tail on your t so they don't look like plus signs. Now what we're going to do is we're going to find two derivatives of this so I can plug it into this differential equation. So we have to find the first derivative, y sub g prime, is 2at plus b, and then y sub g double prime is just 2a. And that's going to go in right there. We're going to rewrite this. We have y double prime, which is 2a, plus 9 times y, and y is at squared plus bt plus c. And we want this to be equal to t squared minus 2t. Okay, I'm going to distribute the 9 and reorder by power of t. So if I distribute the 9, we have 9at squared plus 9bt plus 9c plus 2a. And this has to be equal to t squared minus 2t. And we're going to equate coefficients. So there's an implied 1 right in front of this t squared. So the coefficient of t squares have to be the same. So I'm going to color code them red. The coefficient of the t's have to be the same, including that negative. So 9b, let's color code that with green. And then there's an implied plus 0 over here. And so the constant has to match the 0. Let's make those blue. So when you equate the coefficients, you're going to be able to determine what a, b, and c are, so that all of this comes out to be true. All right, so the reds, 9a has to be 1. The greens, 9b has to be negative 2. And then the blues, 9c plus 2a has to be 0. And we solve the system for a, b, and c. We can clearly see that a is 1/9, b is negative 2/9, and that's going to help us find c, because a is 1/9. So we have, this tells us that if I subtract the 9c and divide by 2, that a is equal to negative 9c over 2. And we know it, sorry, a is equal to, that's not what I wanted to do. I wanted to solve for c. Silly me. Solve for c. c is equal to negative 2a over 9. And since a is 1/9, this will be negative 2/81. So our particular solution is y sub g is equal to a 1/9 times t squared plus b is negative 2/9 times t, and then plus c, and c is negative 2/81. Now we can construct the general solution. The general solution will be the y sub g, so this part. Copy, paste. There's our particular solution to the inhomogeneous portion of our differential equation, the inhomogeneous version, plus arbitrary constant times our first linearly independent solution to the homogeneous version. So that's going to be a cosine 3t plus an arbitrary constant times the second solution to our homogeneous solution, c2 times cosine 3t. And now we've constructed a general solution. Now, of course, if there had been some initial data as well, then I would now have to figure out what C1 and C2 are. So I'm still not out of the woods if I'm looking for a particular solution that satisfies certain initial conditions. So these can get very time consuming. Next one, 8t times e to the 2t. And let's do our characteristic polynomial. Lambda squared plus 3 lambda minus 10 is equal to 0. This factors lambda minus 5 or plus 5 times lambda minus 2 is equal to 0. So that gives me two real roots, negative 5 and 2. Real and distinct. Okay, now look at our structure of the forcing function. We have a polynomial, first degree, times an e to the 2t. Well, that 2 is the r, and it matches one but not both of our roots. So that means, and as far as our table is concerned, we're in this realm right here. We have a polynomial times e to the rt, and our r matches one but not both roots. So we're going to have to do an arbitrary polynomial that matches the degree of this p, e to the rt, and then with an extra t in front. Here we go. So our y sub g will be an extra t in front times a polynomial of first degree that's arbitrary, so at plus b, times the e to the 2t. I'm going to distribute the t through. So it's at squared plus bt times e to the 2t. Now we've got to do some derivatives, and this is where this has potentially to get quite complex, because we have to do a first derivative and a second derivative, so I can do some substitutions, and we're going to have to do a bunch of product rules. First product rule, derivative of the first times the second plus the first times the derivative of the second. Now it might be helpful to combine these into one statement. Factor out the e to the 2t and see what can be combined. I'll put the at squared first. Then we have a bt and a 2at, which can't be combined. And then oh, I forgot to double. Don't, silly me, I almost forgot that 2 there. That's going to double. So we're actually going to have 2 at squares plus 2 bt's, and then plus the 2at that's there. Okay, then plus the b. That's the only thing I don't have yet. Plus the b, and then the e to the 2t factored out. So there's my first derivative. Now we've got to do a second derivative. Again, product rule. Derivative of the first. 4at plus 2a plus 2b times the second plus the first times the derivative of the second. Okay, so there's our second derivative. And now we get to plug these into our differential equation. So y double prime. I'm just going to copy some of these things. All of that alone is y double prime. That's just this part right there. Plus 3 times y prime. So plus 3 times y prime. Y prime is this, so I'm going to copy that. Too many parentheses, there we go. Then we have to do minus 10 times y. So minus 10 times y, and y is right here. Too many parentheses again, there we go. And all of this is equal to 8t e to the 2t. Boy, what a mess. We can certainly divide away the e to the 2t's everywhere. We don't need to write those parts any longer. And then we want to start combining all the similar terms that we have over here. Oh boy, here we go. So I'm going to do some color coding here just to make sure I don't miss anything. I'm going to underline all my t terms. In orange, all my constant terms in red. That's that. And then in green, all of the t squared terms. I think everything is accounted for. Okay, now by color coding, let's do the greens first. All the t squares. So we have 2at squared plus 2at squared plus... Oh, don't forget to distribute these 3's and negative 10's as well. So we have 2at squared plus 6at squared. Oh, I almost made a mistake again. There's another 2 right there. So we've got to be extremely careful here with this. All right, so this 2at squared is times the 2, so it's 4at squared plus 6a, so that's 10at squared, minus all the greens canceled. I'll leave that to you to verify. All the greens cancel. Let's go to the oranges next. We have a 4at plus an... Don't forget, this is multiplied by 2, so plus another 4at. So that's 4at plus 4at is 8at plus another 6at, and that's going to be 14at. And that's not all of the oranges, though. That's just the ones that had A, because we still have this 2bt, or we have a 4bt right here, plus a 6bt, that's a 10bt, minus a 10bt. So those cancel. So all the oranges combined to be 14at. Let's write it this way. I'll underline the greens. So all the greens became 0, all the oranges became 14at. And now let's do all the reds. Let's do the reds and the B's. We have a 2B plus a 2B. So that's 2B plus 2B, that's 4B plus 3B. So I think we get 7B. And then we have a 2A. That 2A right there. And those are all the reds. Okay, and then the other side. After we just get the 8t, because the e of the 2t's all canceled. Factored it all out and divided. Okay, I'm obviously doing a lot of work in my head here because I realize I have a limited space on this particular slide, but I highly recommend you show all your steps, even though it means a lot of writing, just to make sure you don't miss anything. And I'm crossing my fingers that I did not miss anything here. Okay, now we got to equate coefficients. So in front of the t has to match in front of the t. So the 14a has to be 8. And then the constant, 7b plus 2a, has to be equal to the constant over here, which there's an implied 0. There's no constant. So we have to get a 0 out of that. And here's how we create our system of equations. So a is going to be 4/7. So we had plugged that into the second equation. So we have 7b plus 8/7 equals 0, so it equals negative 8/7, and therefore b is equal to negative 8/49. Okay, all of this to say that our y sub g is equal to t times at, a is 4/7, plus b, so minus 8/49, times e to the 2t. And there is our particular solution that satisfies this inhomogeneous differential equation. Now to create a more general solution so that we can go through, satisfy any given initial conditions, which there aren't any in this problem, but in case there were, our general solution is found by doing this particular solution, copy and paste that right there, plus an arbitrary constant times our y1. Our y1 is going to be created by doing e to the lambda t for our first lambda, so e to the negative 5t, and then plus a second constant times e to the lambda t, where lambda is 2. And right there we have our general solution now. You would just have to find C1 and C2 depending on what initial conditions were presented. All right, this one. Y double prime minus 4, let's get our lambdas first. Y squared, lambda squared minus 4 lambda plus 4 is equal to 0. This factors lambda minus 2 times lambda minus 2. All right, so we get lambda is equal to 2 and 2. Now our forcing function is sine 2t. So we are looking at this category in our table where b is a 2 and a is a 0. And then we have a 0-degree polynomial, or a 0-degree constant polynomial in front. Right, did I say that correctly? Yes, 3 in front. And furthermore, because our forcing function forces this solutions to be 0 plus or minus 3i, so our lambdas are not imaginary at all. They're real. So our lambdas, which are, was it 2 and 2, do not equal a plus or minus bi, where a and b come from our forcing function. They do not equal. So we're looking at this category right here. So we're going to create a trial solution by using what's currently circled. The Q1s are going to have to be arbitrary 0-degree polynomials, the Q1 and Q2. The a will be 0, so we have e, so the e parts will be gone. So we just have the cosine and sine that we have to worry about. So our y sub g will be an arbitrary 0-degree polynomial, a, times cosine of 2t, plus an arbitrary polynomial, degree 0, so just b, times sine 2t. Right? If this is missing an exponential, then these will be missing an exponential. And the only thing we had to determine is whether or not I needed to put an extra t in front of each of these, but I do not, because our lambdas, which are just 2 and 2, do not equal 0 plus or minus 2i. Okay, with that said, we've got to get some derivatives. Yg prime is equal to negative 2a sine 2t, and then the next derivative here will be 2b cosine 2t. And then we got to do a second derivative, yg double prime. We get negative 4a cosine 2t minus 4b sine 2t. And now we plug these into this differential equation. So let's start with y double prime. So I'm just going to copy this. Then we have minus 4 times, and we have y prime. Y prime is right here, so let's copy that. Then we have plus 4 times y, and y is right here. Copy and paste that over. There we go. So all of this has to be, in the end, equal to the forcing function, 3 sine 2t. So the best way with the sines and cosines in the mix is to gather all your sine terms together and all your cosine terms together, and then match coefficients of sine and cosine. So I'm going to do color coding again. I'm going to underline all my cosine terms and get them together. And then all the sine terms, we'll get them together. So let's do cosine first. I'm going to factor out the cosine as well. So we have a negative 4a. That takes care of this one. The next one is negative 4 times 2b. So we have a negative 8b. And then the next cosine is a positive 4 times a, plus 4a. And all of that is times cosine of 2t. And all of that is the orange. Okay. I'll give myself just a little bit more space. Move that over slightly. Over slightly. Okay, next, let's gather the reds together, all the signs. So we have, I'm going to put a plus and then parentheses. So we have a negative 4b in front of this sign, so negative 4b. We have a positive 8a in front of a sign. And we have a positive 4b. And that's in front of these are all with the sign 2t. And that's all the reds gathered. And then I hate doing these lines like this. Maybe I can do this. Squeeze that in. And all of that has to be equal to 3 sine 2t. Okay, next. Notice that there is no cosine in our forcing function. So this part has to zero out, which means that the coefficient of the cosine has to be 0. And the negative 4a and the 4a already cancel, so we just get negative 8b has to be 0. And then for this coefficient of sine, the coefficient of sine is 3 on the forcing function, so this coefficient has to be 3. Well, notice the 4b's cancel, so 8a has to be 3. And this gives me b is 0 and a is 3/8. So that means my particular solution, y sub g, is equal to a is 3/8. So 3/8 cosine of 2t. I'm just copying this now with the correct a and b is 0, so that just goes away. So there it is. There is my particular solution for this one. And next, we're going to construct the general solution. Y of t is equal to the particular solution, 3/8 cosine 2t, plus an arbitrary constant in front of, we have our e to the lambda t, so e to the 2t, plus, now we have a repeated lambda, so we have to do a c2 times, like we did before, c2 times t, e to the 2t. And here we have the general solution. All you need now are initial conditions to find what C1 and C2 are, which we won't do here. And then finally, one last slide. This is demonstrating the superposition principle, which was the very last entry in this table right here. Saying if you create a forcing function out of other forcing functions for which you had already found particular solutions, then in the way that you combine them to make a new forcing function, you just combine the particular solutions in the same way. So notice that this first one here, and here we're not looking for general solutions here, we're looking just for the y sub g. That's all I'm after right now, just what the y sub g is. I'm not trying to create the general solutions to any of these. So the y sub g is what we're after. And this first one is one that we had already done. It was the very, very first one. Right here. Exact same differential equation. And we already have a y sub g, so I'm just going to copy this. And so we don't have to do that twice. And paste that right there. So there's our y sub g. And we have 3 different examples here. Notice that the left sides are all the same. It's just the right sides that are different. So I'm going to call these forcing functions all different letters. Let's call this one f, actually. This one h. And this one over here will be our g. So that I should call this one here y sub f, not y sub g. Okay, now let's find our y sub h, this middle one. Well, h is just a first degree polynomial, so y sub h will have the general form at plus b, which means y sub h prime is just a, and y sub h double prime is 0. Now I'm going to plug these into this differential equation. This should go pretty fast. We have 0 plus 3, just a, plus 2 times at plus b, and this has to equal 2t when all is said and done. So we have 2at plus 2b plus 3a have to be equal to 2t. Matching coefficients, that tells me that 2a has to be equal to 2, and that 2b plus 3a has to be equal to 0. For these two polynomials to be the same, which means a has to be 1, and if a is 1, then b is going to be negative 3/2. Oops. That's not what I want to do. I just wanted to separate those slightly. So that tells me my y sub h is a t, so just t plus b, which is, so t minus 3/2 is my y sub h. So now I have a new forcing function over here. But notice it's made up of combining forcing functions for which I had already found particular solutions. So g over here is the same thing as 1/2 of the h function, right? Because the h function was 2t. And this part here, we're subtracting 12 times e to the negative 3t. Well, this f was 4 e to the negative 3t, so we're subtracting 3 f's from this. Right, so my g is really 1/2 h minus 3 f's. So since I've already done the work for finding y sub f and y sub h, in order to find y sub g, we can use that superposition principle and just do 1/2 y sub h minus 3 y sub f. Right. However it is, h and f are combined to make g. You do the same combination to the particular solutions to create the particular solution for g. And so y sub g, therefore, is going to be 1/2 of y sub h. So that's going to be 1/2 of t minus 3/2, and then minus 3 times y sub f. And y sub f was 2e to the negative 3t. So in other words, y sub g will wind up being 1/2 of t minus 3/4 minus 6e to the negative 3t. So we can get this forcing function by combining the forcing. So we can get this particular solution for this forcing function by combining the particular solutions of these two forcing functions. All right, there's a lot to digest there, a lot of tedious calculation by hand that's possible when you're doing this method of undetermined coefficients in order to solve inhomogeneous linear second order linear inhomogeneous ODEs with constant coefficients. And that wraps up topic 15.